The story of Niels Bohr begins in the quiet yet intellectually vibrant city of Copenhagen, Denmark, a place where the air was thick with curiosity and ideas. It was here, on October 7, 1885, that a boy was born who would one day redefine how humanity sees the building blocks of the universe. His name was Niels Henrik David Bohr. From the very start, the world around him seemed to whisper questions rather than answers. His home was not an ordinary one. It was a household filled with books, discussions, and deep respect for learning. His father, Christian Bohr, was a professor of physiology at the University of Copenhagen, a man of great intellect and warmth who spent his life studying the mysteries of life itself. His mother, Ellen Adler Bohr, came from a wealthy and cultured Jewish family known for their love of the arts and education. Between science and culture, between logic and imagination, Niels Bohr grew up in a world that taught him to think and to wonder. As a child, Bohr was not loud or attention-seeking. He was thoughtful, quiet, and endlessly curious. He would often spend hours examining how things worked, tinkering with small instruments or experimenting with objects he found around the house. His father's laboratory became his playground. In that small space filled with glass tubes, chemicals, and curious instruments, Niels learned the power of observation. The sights and sounds of bubbling liquids and shining metals fascinated him. The young boy began to develop an eye for precision, a habit of questioning, and a belief that nature, no matter how complex, could always be understood if one looked closely enough. Bohr's education was deeply influenced by his family environment. His father believed that the best way to teach was not to give answers, but to encourage questions. At the dinner table, discussions about science, philosophy, and art flowed freely. His younger brother, Harold Bohr, who would later become a famous mathematician and even play soccer for Denmark in the 1908 Olympics, shared this atmosphere of open-minded curiosity. The Bohr home became a meeting point for academics, musicians, and thinkers, a place where young Niels learned to see knowledge not as a fixed structure, but as a living, breathing pursuit. When Bohr entered school, his teachers quickly noticed his talent for mathematics and physics. Numbers seemed to come alive in his mind. He had a natural ability to visualize problems and think abstractly. But Bohr was not a student who merely memorized facts. He wanted to understand the why behind every phenomenon. His notebooks were filled not just with solutions, but with questions and observations. Even as a teenager, he began conducting small experiments in his spare time, some of which would impress his teachers and later be published. In 1903, Niels Bohr entered the University of Copenhagen to study physics. At that time, physics was undergoing a transformation. The classical ideas of Newtonian mechanics had long been the foundation of science, but cracks were beginning to appear in its certainty. The mysteries of electricity, magnetism, and radiation were revealing new phenomena that the old laws couldn't fully explain. The discovery of the electron by J.J. Thomson in 1897 and the experiments of Ernest Rutherford on atomic structure were stirring the scientific world. Yet, these developments were only faint echoes in Copenhagen, far from the major centers of scientific research like Cambridge or Berlin. Still, Bohr was fascinated. He was drawn to the atom, that mysterious, invisible entity that held within it the secrets of all matter. At the university, Bohr was known not just for his brilliance but for his deep thoughtfulness. He was not a man of quick answers. When asked a question, he would often pause, sometimes for a long time, thinking carefully before responding. But when he spoke, his words carried clarity and depth. His professors saw in him a rare combination of imagination and logic. He was inspired by the works of Lord Kelvin, Maxwell, and later Rutherford, who were all trying to uncover the hidden structure of matter. But Bohr wanted to go further. He wanted to understand not just what atoms were made of, but how they behaved. In 1906, while still a student, Bohr entered a university competition organized by the Royal Danish Academy of Sciences. The challenge was to investigate a scientific question experimentally, and Bohr chose to study how water's surface tension affects the vibration of small jets of water. It might have seemed like a simple topic, but Bohr's approach was extraordinary. He built delicate glass apparatuses with his own hands and conducted meticulous experiments, using mathematical precision to interpret the results. His report, written in Danish, was so detailed and accurate that it earned him a gold medal. More importantly, it revealed something essential about his character: an obsession with precision, a refusal to accept approximations, and a relentless drive to connect theory with experiment. This experience strengthened his belief that nature's secrets could be revealed through careful observation and deep thought. It also marked the beginning of his lifelong fascination with how the unseen forces of nature shape the physical world. The atom, to him, was not merely a theoretical concept, it was a puzzle, a living mystery that demanded to be solved. Bohr often said that to truly understand something, one must be willing to let go of all assumptions and see the problem from every possible perspective. After completing his undergraduate degree, Bohr continued his studies in physics and earned his master's degree in 1909, followed by his doctorate in 1911. His doctoral dissertation focused on the electron theory of metals, an area where classical physics still dominated, but Bohr found inconsistencies. The theory could not fully explain why metals conducted electricity the way they did. His work hinted that something deeper, something beyond classical laws, was at play inside matter. Though his dissertation did not make waves internationally, it revealed a restless mind seeking answers beyond the known. It was also during these early years that Bohr's fascination with the atom began to crystallize. The discoveries of X-rays, radioactivity, and subatomic particles had shown that atoms were not indivisible as once thought. The atom was alive with movement, energy, and mystery. Bohr was captivated. He devoured every new paper, from Thomson's plum pudding model of the atom to Rutherford's experiments revealing a dense atomic nucleus. He realized that within the atom lay a universe of unanswered questions, questions that could redefine all of physics. In 1911, Bohr's academic path took him beyond Denmark for the first time. He received a scholarship that allowed him to travel to England, the heart of the new physics revolution. He first went to the Cavendish Laboratory at Cambridge to work with J.J. Thomson, the man who had discovered the electron. But Bohr's time there was difficult. Thomson, though a great scientist, was deeply attached to his own model of the atom and skeptical of new ideas. Bohr's attempts to discuss theoretical ideas were met with polite dismissal. For Bohr, it was frustrating but not defeating. He was learning that science was not just about equations, it was about courage. The courage to challenge authority and question the most established truths. A few months later, Bohr moved to the University of Manchester, where he met Ernest Rutherford. This meeting changed his life forever. Rutherford had recently proposed a revolutionary model of the atom based on his famous gold foil experiment. He suggested that atoms consisted mostly of empty space with a small, dense, positively charged nucleus at the center and electrons orbiting around it. But even Rutherford's model had problems. If electrons were orbiting the nucleus like planets, classical physics said they should lose energy and spiral inward, causing the atom to collapse. Yet atoms clearly did not collapse. Something was missing. Bohr was determined to find out what it was. Working with Rutherford in Manchester was a revelation. Here was a man who, like Bohr, was driven by curiosity and boldness. Rutherford's experiments were masterpieces of precision, and Bohr admired his ability to link observation with insight. But Bohr's mind worked differently. He was a theorist at heart, a thinker who sought patterns behind the data. While Rutherford was busy smashing atoms and detecting their fragments, Bohr was quietly trying to understand why those fragments behaved the way they did. In their conversations, Rutherford often joked about Bohr's tendency to think too much, but he also respected his deep intellect. In Manchester, Bohr began to feel the pull of something entirely new. He sensed that the key to understanding the atom lay in a strange new concept: quantization. He had read about Max Planck's theory that energy comes in discrete packets called quanta, and Albert Einstein's idea that light itself might behave like particles. Could the same idea apply inside the atom? Could electrons occupy only specific energy levels rather than any position they pleased? These questions haunted Bohr. Every evening, after long hours in the lab, Bohr would walk through the quiet streets of Manchester, lost in thought. The world outside seemed ordinary: factories, trains, the hum of industrial life. But inside his mind, a revolution was brewing. He imagined the atom not as a miniature solar system, but as something far more mysterious: a quantum system, governed by rules beyond human intuition. The seeds of the quantum revolution were being planted in those long, silent walks. But beneath his calm exterior, Bohr struggled with uncertainty. He often doubted his own ideas and worried that he was chasing illusions. Yet this humility became one of his greatest strengths. Bohr believed that true understanding comes not from certainty but from questioning, from embracing doubt as part of discovery. Later, he would tell his students that the opposite of a profound truth may also be a profound truth, a statement that perfectly captured the paradoxical beauty of quantum mechanics. By the time Bohr returned to Denmark in 1912, he was no longer just a young physicist. He was a thinker standing on the edge of something immense. His experiences in England had given him both frustration and inspiration. He had seen the limits of classical physics, and he knew the path forward would require courage to break from tradition. The atom, once thought to be a solid, indivisible sphere, was now a world of energy and uncertainty. And Bohr, the quiet young man from Copenhagen, was ready to step into that world. In the years to come, he would build on Rutherford's model, combine it with Planck's quantum ideas, and produce the revolutionary atomic model that would change science forever. But before that moment of triumph, there was this: a long journey of curiosity, struggle, and imagination. Bohr's early life was not marked by sudden brilliance but by a steady, burning passion to understand. He was a dreamer of the invisible, a seeker of truths too small to see but too great to ignore. His fascination with the mysteries of atoms was not just a scientific pursuit, it was a calling, the beginning of a revolution that would forever alter humanity's vision of the universe. When Niels Bohr returned to Copenhagen in 1912, he was carrying something invisible but powerful, a new way of thinking about the atom. His time in Manchester had not only expanded his knowledge but awakened his creative courage. The young scientist, barely in his late 20s, felt an unstoppable urge to understand what lay beyond the boundaries of classical science. He was calm on the surface but electric within, a man whose mind was constantly alive with possibilities. Copenhagen at that time was not a global center of physics. There were no great laboratories like those in England or Germany, no stream of brilliant students from across the world. Yet Bohr was determined to make it one. He accepted a position at the University of Copenhagen and began his quiet, solitary work on the structure of the atom. Every night, he would sit at his desk surrounded by papers, equations, and a faintly flickering lamp, lost in thought. His wife Margaret, whom he had married that same year, would often see him completely absorbed, pacing the room, scribbling, erasing, and staring out of the window, as if trying to see the invisible patterns that governed matter itself. Margaret became more than a companion; she was his intellectual anchor, the listener who helped him organize his chaotic, brilliant mind. He often said that she understood him better than anyone else. When Bohr spoke, he had a peculiar habit of starting a sentence, pausing midway, and then reformulating it entirely, as if wrestling his own thoughts into clarity. Margaret patiently followed every pause, every hesitation, every burst of sudden realization. Together, they formed a partnership that balanced deep intellect with humanity. As Bohr continued to think about the atom, he couldn't shake off the image of Rutherford's model: electrons whirling around a dense nucleus. It was elegant yet flawed. According to classical electrodynamics, an accelerating charged particle like an electron should emit radiation continuously, losing energy and spiraling into the nucleus. But atoms were stable. They did not collapse. Why? This question became an obsession for Bohr. He began to realize that the laws of classical physics, the laws of Newton and Maxwell, might not apply inside the atom. He found inspiration in Max Planck's quantum hypothesis, which proposed that energy could be emitted or absorbed only in discrete amounts, called quanta. If that were true for radiation, could it also be true for electrons within the atom? Could the atom itself be quantized? Bohr began to imagine a strange world where electrons could exist only in specific orbits, each corresponding to a particular energy level. When an electron jumped from one orbit to another, it would emit or absorb energy equal to the difference between those levels. That, Bohr thought, might explain the mysterious spectral lines, the fingerprints of atoms, that scientists had observed but never fully understood. The more he calculated, the more sense it made. The hydrogen atom, the simplest of all atoms, seemed to follow this pattern perfectly. Bohr realized that his model could mathematically predict the exact wavelengths of light emitted by hydrogen. It was an astonishing moment, the invisible architecture of matter suddenly revealed through numbers and reason. In 1913, Bohr published his famous trilogy of papers, collectively titled On the Constitution of Atoms and Molecules. These papers, written in precise but visionary language, marked the birth of modern atomic theory. They described a world where the laws of the microscopic realm were not continuous but quantized, where energy came in steps rather than flows. The Bohr model of the atom was born, an elegant fusion of Rutherford's nuclear concept and Planck's quantum idea. At first, the scientific community was stunned. Some were skeptical, others fascinated. The idea that electrons could jump between energy levels without passing through intermediate states sounded absurd, even magical. Yet the mathematics worked perfectly. The spectral lines of hydrogen matched Bohr's calculations with stunning accuracy. The impossible had become possible. Rutherford himself, though initially doubtful, praised Bohr's courage and insight. "It seems to me that you may have done something very big," he reportedly told Bohr after reading his paper. Einstein, too, was impressed, though he would later challenge Bohr on philosophical grounds. Within a year, the Bohr model had spread across Europe, inspiring a new generation of scientists to explore the strange quantum world. But behind this scientific triumph was a man still haunted by questions. Bohr was never fully satisfied with his own theories. He felt that every answer opened new mysteries. How exactly did electrons jump? What determined their behavior? Was there a deeper reality behind the mathematics? He began to suspect that human language and logic might never fully describe the atomic world. This humility, this awareness of the limits of human understanding, became the core of Bohr's philosophy. The years that followed were filled with both struggle and creation. Bohr's fame grew rapidly, but he remained deeply modest. He disliked personal attention and preferred quiet collaboration. In 1920, the University of Copenhagen established the Institute for Theoretical Physics, later known as the Niels Bohr Institute. It quickly became a center of global physics, attracting brilliant young minds from around the world: Werner Heisenberg, Wolfgang Pauli, Max Dilbriquet, and many others. These students and colleagues found in Bohr not just a teacher, but a mentor, a philosopher of science who encouraged them to think freely and challenge assumptions. Within the walls of the institute, discussions would often go late into the night. Bohr would sit among his students, his eyes thoughtful, his voice soft, as he guided them through the paradoxes of quantum theory. He believed that true learning came from dialogue, from questioning and counter-questioning. He rarely dictated ideas. Instead, he asked questions that forced others to think deeply. Sometimes his students left those discussions more confused than before, but later, as they reflected, they realized Bohr had led them to profound insights. Even as he became a global figure, Bohr's fascination with the atom never diminished. To him, the atom was not just a physical object, it was a symbol of mystery, a key to understanding the relationship between knowledge and reality. he began to explore the philosophical meaning of quantum mechanics, introducing the idea of complementarity, the concept that particles can exhibit contradictory properties, such as behaving both like waves and particles, depending on how they are observed. This was not just a scientific principle, but a philosophical truth. Bohr believed that nature revealed itself in ways that depended on our methods of inquiry. Observation was not passive, it was part of the phenomenon itself. This radical idea challenged not only science but philosophy. It suggested that reality was not fixed but dependent on interaction. Einstein famously resisted this interpretation, insisting that God does not play dice. Bohr, with his characteristic calm, replied, "Einstein, stop telling God what to do." It was a moment that defined the new era of physics, an era where certainty was replaced by probability, and reality became a dance between what is and what is measured. Yet, even amidst such groundbreaking thought, Bohr remained a deeply human figure. His colleagues often spoke of his warmth, his sense of humor, and his remarkable patience. Despite his fame, he continued to live modestly in Copenhagen, spending time with his wife and 6 sons. His home was always open to students and visiting scientists, where discussions of physics blended with laughter and stories. There was an almost spiritual quality to his presence, a sense that science, for him, was not just about knowledge, but about understanding our place in the cosmos. As the world outside grew darker with the approach of World War II, Bohr's scientific and moral convictions were tested. Being of partial Jewish heritage through his mother, he became a target when Nazi forces occupied Denmark in 1940. In 1943, facing imminent danger, Bohr and his family fled the country. They were smuggled across the sea to Sweden in a small fishing boat under cover of night. From there, Bohr was flown to Britain, and eventually to the United States, where he contributed to the Allied efforts in science during the war. But even in those turbulent years, Bohr never lost sight of the ethical dimension of science. After witnessing the destructive power of nuclear weapons, he became a strong advocate for the peaceful use of atomic energy and for international scientific cooperation. He believed that knowledge should unite humanity, not divide it. His experience of seeing scientific discovery turned into a weapon of mass destruction left a deep mark on his soul. He spoke passionately about the need for openness, transparency, and dialogue between nations. In his view, just as electrons could not be understood without considering their context, human beings could not exist in isolation from one another. When Bohr returned to Denmark after the war, he resumed his work at the Institute, which had survived the occupation. The post-war years brought him great respect and recognition. He received numerous awards, including the Nobel Prize in Physics in 1922, but these honors mattered little to him compared to the pursuit of truth. He continued to mentor new generations of physicists, emphasizing that science was not a collection of facts, but a process of continual questioning. As he grew older, Bohr's fascination with the atom evolved into a broader curiosity about life and thought. He began to see parallels between quantum mechanics and human experience, between uncertainty in physics and uncertainty in life. To Bohr, both required humility, patience, and openness to paradox. His writings from this period blend science and philosophy, showing a man who had moved beyond equations into the realm of wisdom. Those who met him in his later years often described the quiet intensity of his gaze, the way he would listen more than he spoke, and the way he made others feel that their thoughts truly mattered. To him, every conversation was a form of discovery, every disagreement an opportunity to refine understanding. Even when his ideas were challenged, he welcomed it. He once said, "Every valuable human being must be a radical and a rebel, for what he must aim at is to make things better than they are." This spirit of constant evolution defined both his science and his life. Niels Bohr passed away in 1962, but his presence never truly disappeared. His theories laid the groundwork for the modern world, for quantum mechanics, for nuclear physics, for technologies that define our daily lives. But beyond the equations, Bohr left something deeper, a philosophy of knowledge, a belief that truth is not fixed but grows through dialogue and understanding. Looking back, the seeds of all this were planted in his youth, in that Copenhagen home filled with books and curiosity, in the boy who tinkered with instruments, in the student who questioned every assumption, and in the young man who dared to challenge the giants of physics. His fascination with the mysteries of atoms was not simply a scientific interest, it was a lifelong quest to understand the hidden patterns of existence itself. Today, every time a scientist studies quantum systems or engineers design a quantum computer, the spirit of Niels Bohr is present, the quiet reminder that even the smallest particle can contain infinite wonder. The quantum revolution, in many ways, was born from that curiosity, from a boy who looked into the invisible and refused to look away. His journey from the quiet streets of Copenhagen to the frontiers of atomic theory remains one of the most remarkable stories in the history of science. The legacy of Niels Bohr is not only in the equations that bear his name, but in the mindset he gave to the world, the courage to question, the humility to accept uncertainty, and the imagination to believe that reality is more mysterious than we can ever fully know. In every sense, his early fascination with atoms became a mirror of humanity's deepest drive, the desire to understand the unseen, to reach beyond the visible, and to touch the infinite. In the early years of the 20th century, physics stood at a crossroads. The universe that Isaac Newton had so elegantly described in terms of motion, forces, and gravity seemed complete, predictable, and absolute. Yet, at the smallest scales, within the mysterious world of the atom, this grand order began to crumble. Strange new discoveries hinted that the rules governing the cosmos did not apply to the tiny particles of matter. It was a time of confusion and excitement, and among those who would dare to challenge the old certainties was a young Danish physicist named Niels Bohr. By 1912, Bohr had already glimpsed a problem that had haunted scientists for years. The atom, once thought to be solid and indivisible, had been revealed as a complex structure. Experiments by Ernest Rutherford had shown that most of an atom's mass was concentrated in a tiny central nucleus, with electrons orbiting around it like planets around the sun. But there was a fatal flaw in this model. According to the laws of classical physics, an accelerating charged particle, like an electron, should continuously emit energy in the form of radiation. This energy loss would cause the electron to spiral inward and eventually collapse into the nucleus. If that were true, atoms, and therefore all matter, could not exist. Yet the world clearly existed. Something was missing, something profoundly different. Bohr returned to this puzzle like a composer returning to an unfinished symphony. His time working with Rutherford in Manchester had planted the seed of an idea that would soon blossom into one of the greatest revolutions in science. He began to think, what if the atom did not follow classical laws at all? What if, deep within the heart of matter, a new set of rules applied, rules that operated in discrete steps rather than continuous motion? The clue came from an idea that had already begun to shake the scientific world: Max Planck's quantum hypothesis. In 1900, Planck had proposed that energy is not emitted continuously, but in discrete packets, or quanta. Einstein later expanded on this idea to explain the photoelectric effect, suggesting that light itself behaves as if it were made of particles, photons. Bohr saw in these theories a new kind of order, one that might also govern the behavior of electrons inside atoms. He began to imagine an atom where electrons could not occupy just any orbit, but only certain allowed orbits, fixed energy levels where they could exist without radiating energy. The electrons, he proposed, could jump from one level to another, absorbing or releasing energy in the form of light. These jumps were instantaneous and mysterious, but they seemed to fit the experimental data perfectly. The key test came with hydrogen, the simplest of all atoms, just one proton and one electron, the hydrogen spectrum. A series of colored lines seen when light from hydrogen gas is analyzed through a prism had long baffled scientists. Each line represented light of a specific wavelength, suggesting that atoms could emit or absorb only certain amounts of energy. Bohr set out to explain this pattern mathematically. Using Planck's constant and his own quantization idea, he derived an equation that predicted the exact wavelengths of hydrogen's spectral lines. The result matched the experimental data with stunning precision. It was as if he had unlocked nature's code. When Bohr published his papers in 1913, 3 in total, titled On the Constitution of Atoms and Molecules, they sent ripples through the scientific world. In those pages, written in careful but daring language, Bohr proposed a vision of the atom that no one had imagined before. Electrons moved in fixed orbits, each orbit corresponding to a specific energy level. When an electron jumped from a higher orbit to a lower one, it emitted a photon of light whose energy corresponded exactly to the difference between the two levels. For the first time, there was a model that explained both the structure and the behavior of the atom. This was not just a small step forward, it was a leap across an abyss. Bohr had combined the structure of Rutherford's nuclear atom with the revolutionary idea of quantization, bridging the gap between classical and quantum worlds. The result was elegant, powerful, and deeply unsettling. The concept of quantum jumps, electrons leaping between energy levels without existing in between, defied every law of classical mechanics. Yet the math worked. The experimental data agreed. Nature seemed to obey these strange new rules. Many scientists were skeptical. The idea that energy could come in discrete chunks and that electrons could vanish from one orbit and appear in another was almost mystical. Even Rutherford, Bohr's mentor, was uneasy. "The theory is certainly very daring," he said, "but the calculations are right." Einstein, who admired Bohr's intellect, acknowledged the brilliance of the model, but worried about its implications for determinism. For centuries, physics had been a science of predictability. Given the initial conditions, one could determine everything that would happen next. Bohr's atom introduced uncertainty, discontinuity, and the idea that nature might make random choices. Yet, the evidence kept growing in Bohr's favor. The success of his hydrogen model could not be ignored. Over time, other scientists extended and refined his theory, applying it to more complex atoms and molecules. The Bohr model became a stepping stone to the full development of quantum mechanics in the 1920s. Werner Heisenberg, inspired by Bohr's ideas, would go on to develop matrix mechanics. Schrödinger would describe the atom in terms of wave functions, and together, they would expand the quantum vision that Bohr had helped bring to life. To understand the revolutionary nature of Bohr's model, one must imagine the world before it. A world where matter was thought to behave like clockwork, predictable and continuous. Bohr's atom shattered that vision. It revealed that nature operates in steps, that energy is quantized, and that even the smallest particles obey strange, probabilistic laws. The atom was no longer a miniature solar system, but a dynamic, quantized structure where the boundaries between existence and non-existence blurred. But Bohr's contribution was not only mathematical, it was philosophical. He realized that the new physics required a new way of thinking. The quantum world could not be described using the same language as the everyday world. To understand atoms, one had to accept that our human intuition was limited. The quantum realm was governed by rules that seemed paradoxical, yet true. Bohr often said that if quantum theory didn't make you uneasy, you didn't really understand it. The year 1913 thus stands as a turning point in the history of science. In that single year, a young Danish physicist reimagined the most fundamental object in the universe, the atom, and in doing so, laid the foundation for the technology and philosophy of the modern age. Without Bohr's model, there would be no understanding of chemical bonds, no development of quantum mechanics, no lasers, no transistors, no computers, no GPS. The entire fabric of modern civilization rests, in one way or another, on the principles he introduced. In the years immediately following his discovery, Bohr became an intellectual beacon in Europe. His model of the atom was discussed in every physics department, debated in every lecture hall, and examined in countless experiments. The scientific world was divided, not in hostility, but in awe. Some believed Bohr had revealed the final truth about atomic structure. Others thought it was only the beginning of something even deeper. Bohr himself remained cautious. He often emphasized that his model was a stepping stone, an approximation of reality, not the final word. Every valuable discovery, he once said, must sooner or later find itself on the frontier of paradox. He understood that the quantum world would continue to challenge human understanding for generations. As news of his success spread, Bohr's personal life remained remarkably humble. He continued his work quietly in Copenhagen, often walking through the streets lost in thought. He was not a man of ego or fame. To him, science was a collective endeavor, a conversation among thinkers searching for truth. His writings from this period reveal a man deeply aware of the philosophical weight of his discoveries. The atom, once the symbol of indivisibility and stability, had become a realm of uncertainty, transition, and wonder. Bohr's model also transformed chemistry. For the first time, scientists could explain why elements emit light of specific colors, why they combine to form molecules, and why the periodic table follows its unique structure. Electrons, arranged in quantized shells, determined the chemical behavior of each element. The periodicity of elements was no longer a mysterious pattern, it was a reflection of the quantum architecture of atoms. Bohr's insights bridged the gap between physics and chemistry, uniting two great branches of science under one elegant framework. And yet, even in the glow of his achievement, Bohr remained restless. He sensed that his model, though successful, was incomplete. It could not fully explain the spectra of more complex atoms, nor did it account for the wave-like behavior of electrons that would soon be discovered. He welcomed these inconsistencies, seeing them not as failures but as invitations to go deeper. For Bohr, science was not a quest for final answers, but for ever deeper questions. In later reflections, he would describe his model as both a triumph and a beginning, the point where classical certainty gave way to quantum mystery. He believed that this transition was more than a scientific shift, it was a transformation in the way humanity perceives reality. The universe, he suggested, is not a static mechanism, but a living, dynamic system of possibilities. At the atomic level, reality is not fixed until it is observed, a concept that would later find expression in the Copenhagen interpretation of quantum mechanics, the philosophical heart of Bohr's legacy. The beauty of Bohr's model lies not just in its equations, but in its courage, the willingness to challenge the most fundamental assumptions about nature. In a world dominated by classical thought, Bohr dared to say that the atom was not what it seemed, that the fabric of matter was woven from discrete, quantized threads of energy. He opened a door into a realm of strangeness and wonder, and through that door, the modern age was born. Even now, more than a century later, the echoes of that discovery reverberate through science and technology. Every laser beam, every LED light, every MRI scanner, and every quantum computer traces its lineage back to those nights in Copenhagen when a young physicist sat before his notes, wrestling with the invisible. His atom was not just a model, it was a revolution. The story of Niels Bohr's atomic model is not merely about equations and experiments, it is the story of human imagination confronting the limits of understanding. It is the story of how a single idea can reshape not only science but the way we see ourselves in the universe. Bohr once said, "We are suspended in language in such a way that we cannot say what is up and what is down." In creating his model, he gave humanity a new language, the language of the quantum world, a language that speaks of uncertainty, probability, and the strange beauty of the unseen. In the years following the release of Bohr's atomic model, the scientific community found itself standing at the edge of a new intellectual frontier. What Bohr had introduced in 1913 was not merely a technical correction to existing theories, it was an entirely new vision of matter-energy, and the invisible architecture of the universe. His idea that electrons existed only in certain orbits and could transition between them through discrete energy exchanges seemed to defy the logic of classical physics. Yet, experimental evidence consistently confirmed the predictions of his model. For Bohr, this was both a scientific triumph and a philosophical awakening. He began to realize that understanding nature required not only mathematical precision, but also a deep humility before its mysteries. The atom was no longer a miniature solar system, it was a stage upon which energy danced in quantized steps, revealing that reality itself was granular and unpredictable at its core. As Bohr continued his research in Copenhagen, his ideas began to spread rapidly through the scientific world. Young physicists were drawn to him, not just for his brilliance, but for the warmth and openness with which he shared his thoughts. His laboratory became a meeting place for the minds that would later define quantum theory. Werner Heisenberg, Wolfgang Pauli, and others found in Bohr a mentor who encouraged debate and exploration. He didn't impose answers, instead, he inspired questions. This atmosphere of creative freedom was essential for the growth of the quantum revolution. Bohr's model of the atom served as the first stepping stone, a conceptual map that guided scientists into a realm where light behaved as both wave and particle, and where electrons existed in states of probability rather than certainty. The beauty of Bohr's atomic theory lay in its simplicity and its daring defiance of convention. Before Bohr, most physicists believed that energy was continuous, that an atom could absorb or emit any amount of it. Bohr challenged this by suggesting that energy came in discrete packets, that electrons could only occupy specific energy levels. This single insight redefined the way scientists thought about atomic structure. It explained the bright lines seen in hydrogen's emission spectrum, lines that had long puzzled researchers. Each color, Bohr revealed, corresponded to a specific quantum leap made by an electron. It was a breathtaking realization. The vivid colors seen in a gas tube were the fingerprints of nature's smallest building blocks, moving between the rungs of an invisible ladder of energy. But Bohr's model also contained profound philosophical implications. If electrons could only exist in certain states, what governed their transitions? Could we predict when an electron would jump from one orbit to another? Classical physics said we should, but Bohr's theory suggested otherwise. The world of the atom was ruled not by certainty, but by probability. This was the first glimpse into the strangeness of the quantum domain, a place where causality blurred, and where observation itself influenced what could be known. Bohr understood that this was not merely a limitation of measurement, but a reflection of reality itself. In his quiet, methodical way, he was laying the groundwork for a new understanding of nature, one that accepted ambiguity as a fundamental truth. As the scientific community debated the implications of Bohr's theory, new experiments began to confirm his ideas. The spectral lines of hydrogen matched his predictions with astonishing accuracy. The success of Bohr's model could not be ignored. It provided the first quantitative understanding of atomic behavior. Yet Bohr himself knew that his model was not the final word. It was a bridge, a transitional framework pointing toward a deeper truth that had not yet been fully revealed. In later years, this realization would lead to the development of quantum mechanics, a more complete and mathematically rigorous theory that built upon Bohr's foundations. But even then, Bohr's vision remained central. His insistence that energy levels were quantized became one of the cornerstones of modern physics. The public, too, began to take notice. Though the language of Bohr's theory was deeply mathematical, the imagery it evoked captured imaginations far beyond the scientific community. The idea that the universe was built from invisible particles leaping between states of energy resonated with artists, writers, and philosophers. Bohr's atom became a symbol of modernity, an emblem of a world that was both rational and mysterious, governed by laws that defied common sense yet revealed profound order beneath apparent chaos. For Bohr, however, this fame was secondary. His focus remained on the pursuit of understanding, on the joy of discovery itself. In the quiet halls of the University of Copenhagen, Bohr often reflected on the deeper meaning of his work. He saw physics not only as a tool to describe the universe, but as a way to connect humanity with its cosmic origins. Every atom, he believed, carried within it a fragment of the universe's story, a record of energy and transformation stretching back to the dawn of time. In this way, studying the atom was like reading a sacred text written in the language of mathematics. To Bohr, uncovering its structure was an act of reverence as much as it was of reason. As more scientists joined the quest to understand the atom, Bohr's role evolved from discoverer to philosopher. He began to ask deeper questions about the nature of reality itself. What does it mean to know something about the world if observation can alter the outcome? Can science ever give a complete picture of reality, or only glimpses of it through the act of measurement? These questions, born from his model of the atom, would later blossom into the philosophical framework known as the Copenhagen interpretation, the heart of quantum mechanics. But even before that formalism existed, the seeds of it were present in Bohr's early thinking. His atomic model was not just a scientific theory, it was the beginning of a revolution in thought. By the early 1920s, Bohr's influence had spread across Europe. Laboratories from Berlin to Zurich began to test and refine his ideas, pushing the boundaries of what was known about atomic structure. Einstein, though skeptical of some of Bohr's conclusions, acknowledged the brilliance of his insights. The two men would later engage in some of the most famous debates in scientific history, debates that shaped the philosophical landscape of the 20th century. Yet, in many ways, Bohr and Einstein shared the same goal: to uncover the fundamental laws that govern existence. Where Einstein sought clarity and determinism, Bohr embraced the strange and probabilistic nature of the quantum world. Both were seekers of truth, walking different paths through the same forest of mystery. Bohr's atomic model eventually became the foundation upon which modern quantum mechanics was built. Even as later theories, such as Schrödinger's wave mechanics and Heisenberg's matrix mechanics, offered more precise mathematical descriptions, Bohr's conceptual framework remained indispensable. His vision of quantized energy levels and stable electron orbits explained not only the structure of atoms, but also the behavior of matter and radiation. Without Bohr, there would have been no pathway to understanding the fundamental forces that shape the cosmos. His work was the bridge between the classical and the quantum, between certainty and mystery. As the quantum revolution gained momentum, Bohr's name became synonymous with the spirit of scientific curiosity and humility. He was not content with easy answers. He sought deeper meaning, even in uncertainty. In this way, his model of the atom was not just a scientific milestone, it was a metaphor for the human condition. Just as electrons move between invisible states, humanity too moves between moments of clarity and confusion, between knowledge and wonder. Bohr taught the world that the beauty of science lies not in eliminating mystery, but in embracing it. Through his atomic model, Niels Bohr gave humanity a new lens through which to see the universe. He revealed that beneath the apparent simplicity of matter lies a world of complexity, governed by laws that challenge our imagination. And yet, in that strangeness, there is harmony. The atom, once thought to be the indivisible core of all things, became a symbol of connection between energy and matter, between observation and reality, between knowledge and awe. It all began with a quiet man from Copenhagen who looked into the heart of the atom and saw not chaos, but order shaped by the dance of quantum energy. His legacy continues to resonate in every experiment, every theory, and every discovery that seeks to unveil the secrets of the cosmos. When Niels Bohr introduced the concept of energy levels and quantum jumps, he not only gave structure to the atom, but also opened a new chapter in humanity's understanding of the invisible forces shaping the universe. Before Bohr's insight, the atom was a mystery clouded in uncertainty. Physicists could describe some of its behavior mathematically, But there were contradictions that refused to vanish. Why did atoms emit light at specific frequencies? Why didn't electrons spiral into the nucleus as classical physics predicted? These questions haunted early 20th century science. Bohr's answer, that electrons occupy specific orbits with quantized energies, was radical. He proposed that when an electron jumps from a higher orbit to a lower one, it emits a photon of energy equal to the difference between the two levels. Conversely, when it absorbs energy, it leaps upward to a higher state. This elegant concept explained the spectral lines of hydrogen, one of the great puzzles of the age. It was a moment of clarity that signaled the beginning of quantum theory as a true science of the microscopic world. In Bohr's atomic vision, energy was no longer a continuous river, it was a staircase with distinct steps. The electron could not move smoothly between levels, it had to leap, a quantum jump. This idea shattered centuries of deterministic thought. The classical world, as defined by Newton and refined by Maxwell, was one of predictability and smooth change. In that world, cause and effect followed each other like clockwork. Bohr showed that at the atomic scale, nature operates differently, not with continuity, but with discontinuity. The atom's energy landscape was divided into discrete realms, and movement between them happened in sudden, indivisible bursts. This was not just a new physical model, it was a philosophical earthquake. It meant that energy, one of the most fundamental aspects of existence, came in packets, not waves, in quantized bits that could not be subdivided. This concept did not come easily. Even Bohr himself struggled to fully believe the consequences of what he was proposing. Yet, experimental evidence was relentless. The spectral lines of hydrogen were not random, they were precise and predictable, matching the equations derived from Bohr's model. Each line in the hydrogen spectrum represented an electron's leap, a fingerprint of the atom's inner workings. What had once been an abstract mystery became measurable, mathematical truth. For the first time, humanity had a model that could explain atomic stability and the emission of light in terms of quantum mechanics. The language of quantum jumps soon became more than a scientific term, it was a metaphor for transformation, for sudden changes that defied gradual explanation. In nature, as Bohr revealed, transformation was not always continuous. The electron's leap symbolized a universe where change happens in discrete acts, where existence can shift abruptly from one state to another. The atom, it seemed, was alive with rhythm and purpose, obeying invisible laws of quantization that defined everything from light to chemistry. Bohr's quantum leaps challenged not only science but human intuition. The notion that an electron could instantaneously move from one orbit to another without passing through the space in between seemed absurd. It violated the smooth, cause and effect logic of classical motion. Yet experiments repeatedly confirmed it. In the strange kingdom of the atom, rules that governed planets and stars no longer applied. Energy appeared in packets, motion occurred in leaps. The universe, Bohr realized, was not a clockwork mechanism but a symphony of discrete notes. At first, many physicists resisted this new picture. The implications were too strange, too unsettling. It meant that the laws of physics could be fundamentally discontinuous, that nature itself operated on jumps and probabilities. Bohr's idea hinted at a reality where determinism was an illusion and where the universe's most basic operations were statistical in nature. Still, the evidence accumulated. The success of Bohr's model in explaining atomic spectra left no doubt. The concept of quantized energy was here to stay. In the years that followed, other scientists refined and expanded upon Bohr's concept. The idea of energy levels became the foundation of quantum mechanics, influencing the work of Schrödinger, Heisenberg, and Dirac. Schrödinger's wave equation described how electrons exist as wave-like entities within these discrete levels, while Heisenberg's matrix mechanics mathematically captured the same phenomenon without referring to electron paths at all. But even as quantum theory grew more complex, the seed planted by Bohr, the idea of energy levels and quantum jumps, remained at its core. For Bohr, however, the true significance of energy levels went beyond equations. He saw in them a philosophical truth about the limits of human understanding. Nature, he realized, does not reveal itself in continuous clarity. There are boundaries, thresholds, and leaps, moments where knowledge must jump as well. He often compared the process of discovery to these quantum transitions, bursts of insight separated by long periods of uncertainty. Just as the electron cannot exist between energy levels, the human mind cannot always bridge the unknown with continuous reasoning. Sometimes, progress happens in leaps of intuition. The concept of quantized energy also had profound implications for the understanding of light. Earlier, physicists like Max Planck and Albert Einstein had introduced the idea of quanta in the context of radiation, energy emitted or absorbed in discrete amounts. Bohr extended this principle into the structure of matter itself. By linking Planck's quantum hypothesis with Rutherford's nuclear atom, Bohr created a synthesis that unified energy and structure. Matter and radiation were no longer separate phenomena, they were two sides of the same quantized reality. This unity became one of the deepest insights of modern physics. Beyond the laboratory, Bohr's ideas began to influence other fields of thought. Philosophers and artists found inspiration in the concept of quantum jumps, in the idea that change could be sudden, that new states of being could emerge without visible transition. The world of the atom mirrored the human experience, unpredictable, discontinuous, and yet governed by hidden order. Bohr's atomic theory resonated with a century already in motion, an age of revolutions in art, thought, and technology. It was as though the atom itself reflected the turbulence and transformation of modern life. Yet Bohr never claimed that his model was complete. He saw it as a provisional step, a bridge toward a deeper truth. Even as he described electrons jumping between levels, he understood that the underlying mechanism was still beyond comprehension. He often emphasized the importance of humility in science, the acceptance that knowledge comes in fragments, that reality may always retain elements of mystery. This philosophical openness became one of Bohr's defining traits and a cornerstone of quantum philosophy. By the time the 1920s arrived, the idea of quantized energy levels had become a cornerstone of atomic physics. Scientists used it to explain chemical bonding, the behavior of metals, and even the colors emitted by distant stars. Each spectral line observed in the heavens became a testament to Bohr's vision, proof that the same quantum rules governing electrons on Earth operated throughout the cosmos. The atom was no longer an isolated unit of matter, it was a universal symbol of connection, linking light, energy, and structure in a single elegant framework. Bohr's quantum jumps also changed how scientists viewed stability. According to classical physics, an accelerating electron should lose energy and collapse into the nucleus, but this did not happen. Bohr's quantized orbits explained why electrons could only occupy specific energy levels and could not spiral inward continuously. This insight explained the persistence of matter itself. Every atom, every molecule, every solid structure around us exists because of these quantized rules. The stability of the world, the endurance of form and structure, arises from the quantum restrictions first proposed by Bohr. For Bohr, the discovery of quantized energy levels was not just a scientific victory, it was a glimpse into the deep harmony of nature. He once described physics as the study of what we can say about nature, not necessarily what nature is. This distinction reflected his belief that our understanding of the universe is shaped by the limits of observation. The electron's leap was not only a physical event, but a symbol of the boundary between what can be measured and what must be imagined. In that mysterious space between orbits, Bohr found a metaphor for human knowledge itself, a reminder that there are realms we can describe only through probability, not certainty. The concept of energy levels also paved the way for technological revolutions. The principles Bohr established underpin much of modern science and engineering, from lasers to semiconductors, from atomic clocks to quantum computers. Every time light is emitted or absorbed in a device, From a neon sign to a fiber optic cable, it echoes the quantum jumps Bohr first described. The universe itself, from the glow of stars to the colors of nebulae, is illuminated by these transitions. In a sense, Bohr's theory did not just explain the atom, it explained light, color, and even the essence of energy exchange throughout the cosmos. Thus, the introduction of energy levels and quantum jumps was far more than a technical solution. It was a philosophical and cultural transformation. It showed that at the heart of matter lies a system of order defined by discontinuity. It revealed a universe that changes not through gradual evolution, but through bursts of transformation, through the rhythm of quantum leaps. Bohr's insight taught humanity that beneath the seeming chaos of the microscopic world lies a perfect, quantized harmony, a symphony written in the smallest measures of energy. In the quiet glow of his Copenhagen study, Bohr often reflected on the paradox his theory had unveiled, that stability is born from discontinuity and that certainty emerges from the unpredictable. The atom, he realized, was both a mystery and a message, a reminder that nature does not follow human expectations, but invites us to broaden them. Through the language of energy levels and quantum jumps, Bohr had given humanity a new way to see the invisible, to measure the unmeasurable, and to find order in the realm of uncertainty. The quantum revolution, in all its strangeness and wonder, began with these leaps. Small, invisible transitions that echo through every atom, every beam of light, and every corner of the cosmos. As Bohr's model matured, the full depth of his concept of energy levels and quantum jumps began to unfold across both scientific and philosophical dimensions. The early resistance that had greeted his idea slowly gave way to widespread acceptance as experiment after experiment confirmed the precision of his theory. Spectroscopy, which allowed scientists to analyze light emitted by different elements, became one of the most powerful tools of the new atomic science. When researchers looked at the light from hydrogen or helium through a prism, they saw distinct lines, the unique spectral fingerprints of each element. With Bohr's explanation of energy levels, these mysterious lines finally made sense. Each line represented a transition, a quantum jump between specific energy states. What had once been abstract symbols became a clear reflection of the atom's inner architecture. For the first time, humanity had a window into the secret rhythm of matter itself. The beauty of Bohr's idea was that it turned the invisible into something tangible. The atom was no longer an unknowable point, it became a structured, living system governed by clear rules. Each energy level was like a rung on an invisible ladder, and the electrons danced upon it according to precise, quantized rhythms. This visualization captured the imagination of scientists and laypeople alike. It provided an image of the atom not as chaos, but as harmony. Bohr's vision gave structure to the microscopic universe, revealing a cosmos where stability emerged from dynamic balance. Even though electrons moved at unimaginable speeds and distances too small to see, their motion followed patterns of perfect mathematical consistency. The simplicity of this order gave birth to a sense of awe. The universe, Bohr showed, was not random, it was quantized, layered, and deeply interconnected. But beneath the elegance of his model lay a revolution in thought. The concept of energy levels introduced a new way to think about the universe, one that accepted uncertainty and discontinuity as natural. Classical physics had long been built on the assumption that all processes occurred smoothly and continuously. Bohr's quantum jumps shattered that illusion. In the quantum world, an electron did not glide from one orbit to another, it leapt instantaneously, without passing through the space in between. That defied every instinct of classical reasoning. Yet, this discontinuity was not chaos, it was the fundamental rhythm of nature. It became a symbol for the limits of human understanding, showing that nature's workings could be precise and ordered, even when they appeared paradoxical. Bohr's contemporaries struggled with the implications. Albert Einstein admired Bohr's brilliance, but was deeply unsettled by the probabilistic nature of quantum behavior. He famously quipped, "God does not play dice with the universe. But Bohr countered with equal conviction, suggesting that perhaps it was not God who played dice. It was human understanding that demanded certainty where none existed. For Bohr, the electron's leap was not random, it followed rules defined by probabilities, not certainties. This distinction became one of the central philosophical battles of 20th century science, shaping decades of debate about the meaning of quantum mechanics. Even as the mathematics of the quantum world became more sophisticated, Bohr remained grounded in the conceptual and philosophical essence of his discoveries. He understood that the true revolution lay not just in numbers, but in perception. To him, the discovery of quantized energy levels was evidence that human logic must evolve to meet the complexities of nature. The old frameworks of cause and effect could not capture the fluid reality of the atomic world. Instead, new principles, such as complementarity, were needed. In Bohr's view, particles could behave as both waves and discrete entities, depending on how we observe them. The quantum jump thus symbolized more than a change in energy, it represented a shift in perspective, a recognition that knowledge itself was intertwined with the act of observation. This realization profoundly influenced the philosophy of science. It introduced a humility that had been missing from earlier centuries of exploration. Bohr often spoke about the limits of language, the idea that words and human logic were insufficient to fully describe the quantum world. He once remarked that when it comes to atoms, language can only be used as in poetry. This was not an admission of failure, but an acknowledgement of mystery. For Bohr, science was not about dominating nature, but about harmonizing with it, about learning to listen to what the universe was whispering through the equations. The quantum jump, with all its unpredictability and precision, became a symbol of that dialogue. As the 1920s progressed, Bohr's model evolved further with the arrival of quantum mechanics proper. Werner Heisenberg, one of Bohr's closest collaborators, developed matrix mechanics, a theory that replaced visual orbits with mathematical relationships between energy states. Schrödinger soon followed with wave mechanics, describing electrons not as particles orbiting like planets, but as standing waves spread through space. These new interpretations refined and extended Bohr's ideas, yet they never erased them. The concept of quantized energy remained central to all later developments. In fact, the very notion of quantum states, the discrete energy levels described by Bohr, became the language of all modern physics. In laboratories around the world, Bohr's energy levels were no longer abstract theories, but the foundation for real discoveries. The development of spectroscopy, atomic clocks, and lasers all traced their origins to the same fundamental principle, that electrons transition between quantized states. When scientists learned to control these transitions, a new age of technology was born. Lasers, for example, rely on electrons jumping between specific energy levels to emit coherent light. Atomic clocks use the precision of these transitions to measure time with incredible accuracy. Every time a digital device synchronizes or a GPS satellite corrects its position, it does so through the legacy of Bohr's energy levels. The influence of Bohr's concept extended beyond physics. In chemistry, the idea of quantized energy levels explained why atoms form specific chemical bonds, why certain reactions occur, and why elements exhibit their characteristic properties. The entire periodic table gained deeper meaning through Bohr's model. Each element's behavior, its colors, reactivity, and stability, was tied to the arrangement of its electrons in discrete energy shells. The microscopic quantum structure of atoms thus shaped the macroscopic world of matter. The colors of metals, the glow of neon lights, the sparkle of stars, all were expressions of quantum jumps, of electrons leaping through the invisible ladders Bohr had described. Even in astronomy, the echoes of Bohr's theory resounded. When astrophysicists examined light from distant stars, they used the same spectral patterns Bohr had explained to identify elements across the cosmos. In a very real sense, Bohr's energy levels became a universal language, a way to read the composition of the universe itself. Every photon emitted from a star, Every glimmer in the night sky carried within it the signature of a quantum transition. Bohr's discovery transformed not only physics but also our cosmic perspective. It showed that the same laws governing electrons in a laboratory in Copenhagen also governed the hearts of stars billions of light years away. And yet, Bohr remained remarkably humble. Despite his global fame, he often spoke with quiet reflection about the limits of human knowledge. He viewed the quantum world not as something to conquer, but as something to coexist with. His insight into energy levels and quantum jumps was, for him, a testament to the profound subtlety of nature, a reminder that the universe is more mysterious than the human mind can easily grasp. He frequently compared scientific discovery to standing at the shore of an infinite ocean, aware that the horizon of understanding would always recede as we approached it. By the later years of his life, Bohr's ideas had become deeply woven into the very fabric of science and philosophy. The concept of quantized energy levels remained the heartbeat of quantum theory, while the metaphor of the quantum jump inspired thinkers in fields as diverse as psychology, art, and theology. It suggested that transformation, whether in atoms or in minds, occurs in leaps, not gradual transitions. It was a concept both scientific and poetic, capturing the mystery of change itself. In every sense, Bohr's idea of energy levels and quantum jumps marked a turning point in human thought. It showed that nature's order was built on discontinuity, that light and matter shared a common quantized language, and that even the smallest particles of the universe contained infinite depth. The quantum jump became the symbol of a world both stable and dynamic, logical and mysterious, a world where the act of observation shaped reality itself. Bohr's genius was not only in discovering this truth, but in recognizing its meaning. The atom, once a static particle of matter, had become a living expression of energy, pulsing, leaping, and forever reminding us that even in the smallest spaces, the universe is full of wonder. Niels Bohr's legacy endures not simply because of what he discovered, but because of how he thought. Through the concept of energy levels and quantum jumps, he taught humanity to see the universe not as a machine, but as a living pattern of relationships, a delicate balance between certainty and mystery. Every light we see, every atom that forms the world around us, and every photon that crosses the cosmos tells the same story, a story that began with a leap, a quantum leap, first imagined by a man who looked into the invisible and found beauty, harmony, and the eternal rhythm of energy itself. When Niels Bohr introduced his revolutionary model of the atom, he didn't just change how scientists viewed matter. He built the foundation of what would become one of the most profound theories in all of science, quantum mechanics. But this new science did not emerge overnight. It was the result of years of exploration, confusion, and collaboration among the greatest minds of the 20th century. Bohr stood at the center of this intellectual storm, guiding, questioning, and inspiring. His work became the cornerstone upon which others, like Heisenberg, Schrödinger, and Dirac, built their own discoveries. Together, they laid the groundwork for a completely new understanding of the microscopic world, a world that defied common sense but perfectly explained how nature truly operates. Bohr's greatest contribution to the birth of quantum mechanics was his vision of the atom as a structure governed not by classical rules, but by probabilities and discrete energy states. He dared to break free from Newtonian certainty, introducing a realm where the laws of cause and effect no longer applied in the same way. This was not an easy idea to accept even for scientists. But Bohr's model explained experimental results that no one else could, and it opened a path for others to extend his theory. His student, Werner Heisenberg, developed the uncertainty principle, an idea that perfectly complemented Bohr's vision by showing that one could never know both the position and momentum of a particle with absolute precision. Schrödinger, inspired by Bohr's quantum levels, formulated his famous wave equation, which mathematically described how particles behave like waves. Bohr's atomic theory had become a spark that lit the fire of modern quantum mechanics. As this new framework began to take shape, Bohr became its philosopher and guardian. He proposed the Copenhagen interpretation, which became the most widely accepted explanation of what quantum mechanics truly means. According to this view, particles do not exist in definite states until they are observed. Reality, in the quantum sense, is shaped by the act of measurement itself. This was a radical and unsettling idea, that observation could influence existence, but Bohr's calm reasoning and intellectual authority made it easier for others to accept. He taught that the quantum world should not be forced into the logic of everyday experience. Instead, science must adapt its language and thinking to fit this new reality. Bohr's influence extended far beyond his own discoveries. His institute in Copenhagen became a hub of innovation where the brightest young scientists of the century gathered. They came from across the world to learn from him, to argue with him, and to explore the mysteries of matter together. The atmosphere was electric, filled with passionate discussions, laughter, and philosophical debates. Bohr encouraged open communication and collaboration, believing that science thrives not on competition, but on shared curiosity. His leadership helped shape a new generation of physicists who carried his ideas forward into the future. The foundation of quantum mechanics that Bohr helped to build did more than transform physics. It redefined reality itself. It taught humanity that nature, at its deepest level, is not mechanical but dynamic, unpredictable, and beautifully complex. It revealed a universe that cannot always be explained in terms of human logic, but one that follows a deeper mathematical rhythm. Bohr's humility in the face of this mystery made him not just a scientist but a philosopher of nature. He once said, "Those who are not shocked when they first come across quantum theory cannot possibly have understood it." This statement captures the heart of his influence, an acknowledgement that truth in science is not always comfortable, but it is always enlightening. Through his ideas, teaching, and quiet wisdom, Bohr gave structure and meaning to a field that might have otherwise remained chaotic. His vision of the quantum world became the lens through which all future discoveries would be seen. The laws of quantum mechanics now govern technologies that define modern life, from semiconductors to lasers, from atomic clocks to quantum computers. All of this traces back to Bohr's courage to question the known and embrace the unknown. The foundation he laid was not just scientific but philosophical, a reminder that understanding reality requires both reason and imagination. Bohr's role in shaping quantum mechanics was not simply that of a contributor, he was its architect, philosopher, and heart. The impact of Niels Bohr's ideas reaches far beyond the era in which he lived. His vision of the atomic world laid the groundwork for countless discoveries that continue to shape modern science and technology. Every corner of the technological landscape, from the smallest microchip to the most advanced quantum computer, carries the signature of Bohr's revolutionary understanding of matter and energy. What began as a theoretical model in his Copenhagen laboratory evolved into a framework that drives modern innovation. The technologies that define today's civilization, such as lasers, semiconductors, nuclear energy, and quantum computing, are all direct descendants of the principles Bohr helped uncover. His concept of discrete energy levels and quantum transitions gave scientists the language to understand how electrons behave, and this understanding became the key to manipulating the physical world at the atomic scale. The modern world of electronics, communication, and computing would be unrecognizable without Bohr's foundation. When transistors were invented in the mid-20th century, they were built upon the understanding of electron behavior within materials, an understanding born from Bohr's quantum insights. The same principles govern semiconductors, which form the heart of every computer, smartphone, and digital device. The laser, another invention rooted in quantum theory, relies on the movement of electrons between energy levels, precisely the mechanism Bohr had described decades earlier. Even in medicine, Technologies like MRI scans and radiation therapy trace their origins back to Bohr's atomic model, which helped scientists unlock the secrets of atomic interactions, the vast network of systems that sustain modern life. Communication, computation, energy, and imaging all whisper the language of quantum mechanics, the language that Bohr helped the world learn. But Bohr's legacy is not just technological, it is intellectual and cultural. His approach to science changed how people think about knowledge itself. He showed that reality is not always something we can predict or control, but something we must learn to understand through observation and humility. This shift in thinking influenced generations of scientists and thinkers. The philosophy of uncertainty and complementarity has inspired artists, writers, and philosophers, offering a metaphor for life's complexity and the coexistence of opposites. In this sense, Bohr's work became more than physics. It became a philosophy of balance, showing that contradiction and harmony can exist side by side. Bohr's influence also shaped how nations approached science and global cooperation. After witnessing the destructive potential of atomic research during World War II, he became a leading advocate for openness and communication among scientists across borders. He believed that knowledge, once discovered, belonged to all humanity and that secrecy only hindered progress. His voice carried weight in the post-war years as he urged world leaders to use atomic knowledge for peace rather than war. His idealism may have seemed utopian, but it reflected the same moral depth that guided his scientific work: the belief that understanding the universe should lead to understanding each other. The ripple effect of Bohr's work continues to expand even in the 21st century. Quantum mechanics has become the foundation of new frontiers like quantum computing and quantum communication. Technologies that promise to redefine information, security, and even artificial intelligence. These fields operate on the very principles Bohr introduced: superposition, uncertainty, and quantized energy levels. In a sense, Bohr's dream of exploring the unseen layers of reality continues through the scientists who now manipulate individual atoms and quantum bits. His ideas remain the guiding compass for those pushing the boundaries of what is possible. Bohr's intellectual courage continues to inspire the scientific spirit. He taught that true discovery begins when one is willing to question even the most established truths. He believed that knowledge grows through doubt, not certainty. This mindset, the willingness to embrace paradox and complexity, has become a defining feature of modern science. His life and work remind us that progress is not a straight path, but a series of leaps across the unknown, guided by curiosity and imagination. The legacy of Niels Bohr is therefore not confined to physics laboratories or university textbooks. It lives in every innovation that arises from the quantum world, in every theory that challenges the boundaries of understanding, and in every scientist who dares to ask questions that seem impossible. His contributions echo in the hum of computers, the glow of lasers, and the data that travel through fiber optic cables across the globe. More than a century after his birth, Bohr's vision continues to define the modern world, not just in the machines we build, but in the way we think about the nature of existence. He taught humanity that the universe is not a machine to be mastered, but a mystery to be understood with wonder. His revolution did not end with his time. It lives on as the heartbeat of every scientific quest that seeks to uncover the secrets of the cosmos.